Welcome back, dear students. In today's session, we'll be discussing classical problem of synchronization. Now here we discuss bounded buffer problem, readers and writers problem, dining philosophers problem. Let us see it one by one. Now bounded buffer problem. Here we assume that we have n buffers and each can hold one item. We are having n buffers and each of these buffers can hold at least one item here. Now here semaphore mutex is initialized to 1. We are using semaphore mutex, and remember mutex is of type binary semaphore. So initially it is set to 1. And semaphore, one more semaphore we are using here as full, which is initialized to 0. Semaphore empty, the third one, initialized to value n here. So here in this bounded buffer problem, we are using three types of semaphores: mutex, full and empty. Now here we have a structure of producer and consumer processes. In producer process, while the condition is true, the producer produces an item. Then it invokes wait on empty semaphore and wait on mutex semaphore. Then adds an item to the buffer. After doing so, it signals mutex and also call a signal function over full semaphore. In consumer code, while the condition is true, it will call for wait on full mutex, then wait on full semaphore, then wait on mutex. After invoking wait on mutex, it removes an item from the buffer. Remember, this is consumer process. So as producer produces an item, then only consumer can invoke a wait on mutex and can remove an item from the buffer. After doing so, it calls upon signal over mutex and signal over empty semaphores so that it consumes the removed item. The next problem here is reader's writer problem. A data set is shared among a number of concurrent processes. Here in reader's writer problem, a set of data elements are being shared among the number of processes that are running concurrently. Some of the processes are termed as readers, whereas others are termed as writers. So readers only read the data set and they do not perform any updates or any kind of manipulation over the data set. Whereas writers can do both. They can read as well as write over the data set. Now the problem here is to allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. So here we can allow multiple readers to read the same data elements that are being shared, but there can only be one and only one writer who is having an access to manipulate the shared data elements. Now shared data include data sets, semaphore mutex, which is initialized to 1, semaphore write, which is initialized to 1 again, and integer read count, which is initialized to 0. Now let us have a close look upon writer's process as well as reader's process. In writer's process, we have this loop, while loop. While the condition is true, wait on writer semaphore is invoked and writer writes the data element. So that means it manipulates the data element here. And then it invokes a signal over this write semaphore. Whereas in case of reader's problem, while the condition is true, wait function is invoked over mutex, then read count is incremented If read count is equal to 1, then again wait over the write semaphore is invoked and following signal over the mutex operation is carried out. It indicates that reading is performed. Then wait over the mutex is executed and read is decremented by 1. If read count is equal to 0, then signal over write mutex is invoked, followed by signal over mutex semaphore. I hope you are able to understand this. This procedure is carried out one by one. Okay. Now the next problem here is dining philosopher's problem. Here you are having a diagram in front of you, which shows the philosophers are sitting over a round table, right? Dining. Each one of the philosopher is having a bowl of rice and chopsticks. See here, in this dining philosopher's problem, there are some shared data. The shared data include bowl of rice, we are calling it as a data set, and semaphore, we are calling semaphore as chopstick, and they are 5 in numbers, whereas there are 5 philosophers sitting here. Okay. Now these 5 chopsticks are initialized to 1, right? And they are having their own plate where they can put some rice and have their meal. So here we have a structure for philosopher, that is philosopher's good. While the condition is true, wait over chopstick I. See, remember we are having chopsticks that are 5 in numbers. Okay, so we are having total 5 chopsticks. Now I can take value from 1 to 5. So wait over chopstick I is performed. Then wait over chopstick I plus 1% 5. That means wait over when this is divided by 5, whatever is remainder, when we are performing wait over that number of chopsticks. Okay, so when once wait is performed, this philosopher can eat. Now there are 5 philosophers and I can have a range of 1 to 5. Okay, so first time if it is 1, then this philosopher can eat, because for eating purpose it needs 2 chopsticks, right? So one chopstick will not do. There is a requirement of 2 chopsticks for eating purpose, for the operation of eating. Then after eating it will put down the chopstick. So putting down chopstick means it is releasing these chopsticks. This chopstick can be released as soon as the signal over the chopstick is invoked. Hence, and it will continue thinking. Now philosophers, they do have a tendency that they goes in thinking phase, right? Whatever they are doing, they just do it and then they think. Then they come back to the work again, then they go in their thinking again. Okay, so this continues. So here, while they are sitting on a dining table, eating and thinking, these are the 2 alternative processes that will be carried out by the philosopher. Okay, so while it is eating, it will pick up the chopstick, will eat and then put down the chopstick and will again go back to the thinking stage. Now here we have a new term, monitors. Like in earlier lecture we have seen that semaphore is a synchronization tool. So here monitors are also playing a role of synchronization tool, and synchronization tool is utilized for the purpose of synchronization, where you have multiple processes running concurrently. Now here we discuss some problem with incorrect usage of semaphore. The semaphore may not give you good performance if the order of signal and wait operations are reversed, and several processes are in their critical section at the same time. So that this actually violates the mutual exclusion property. See, here we have signal over mutex. We know mutex is a semaphore that will have only two values, 0 or 1. So it is also called as a binary semaphore. So here once signal over mutex is indicated, it means it can enter into critical section. Then wait over mutex is applied. Okay, so this is the order, right? If this order is reversed, then the semaphore may not function properly. Also, incorrect use of it may result in an incorrect use when signal call is replaced with the wait call. Then surely there will occur a deadlock. See here, if we just replace this signal function call with wait call, it will invoke a deadlock situation. If we omit wait functions or signal functions, then mutual exclusion property is violated and there is a chance of deadlock occurrence. So in normal section we do not have any problem, but there will be a problem with critical section. Okay, so to avoid this, we can make use of monitors. Now monitors is a high level abstraction that provides convenient and effective mechanism for process synchronization. Here, only one process may be active within the monitor at a time. One and only one process will be active within this monitor at the given time. So here we have a structure for monitors. Here we have a keyword monitor and the name of the monitor we can specify here. And it includes the shared variable declaration. So here you can put the variables that will be used among the processes that are cooperating. You can declare them here. Then you have operations associated with it. Not only the data elements that are being shared by the processes that are cooperating with each other, but here in monitor structure we do have processes associated with it. Okay, so here we have procedures, procedure 1 and their declaration here, procedure 2 and so on, their declaration, and there it also includes the initialization code. So this is the general structure of a monitor. Now here we have a schematic view of a monitor. Here you can see the shared data section is there, then operations associated with this data and initialization code. Now here we have an entry queue. Now these will the processes that wish to enter the critical section, they will be put in a queue here. Okay. Now to make use of monitors we have condition variables. Now for time being, let us assume x and y are the condition variables. That is the variables that are being shared, we are calling them as condition variables again. And the two operations that can occur on this condition variable is wait operation and signal operation. So if it is x dot wait operation, this means that the process which has invoked this operation will be suspended. The process who invokes wait function will be suspended. Okay, and the process who invokes signal function will resume its execution, right? So if x dot signal is invoked, it resumes one of the process that invoked x dot wait. That means whatever, see here we have used the same condition variable x dot wait and x dot signal. So it is the same process. The process who invoked wait first will be resuming here after it has invoked a signal operation. This is the schematic of monitors with condition variables. Now what additional thing we are having here? In the shared data area of monitor, we have condition variables associated with it, and with each of these condition variables we have cues associated. See here, X is having its own cue and Y is having its own cue here, and rest of the thing is the same. Now the problem that we discussed earlier is dining philosopher's problem. To provide a solution to this dining philosopher's problem, we can make use of monitor. So here we declare the structure of monitor as monitor dining philosopher. We just label the name of the monitor as dining philosopher. And here are the some variables. Now these may include thinking, hungry, eating. So there are 5 states here, and we have used one more thing, that is self, condition self. Again we have discussed that it needs 5 chopsticks were there. Okay, so condition self again 5 in number. Then we have here operations associated. What will be the operation? When it is thinking, it will put down the chopstick. When the philosopher is hungry and wants to eat, if is feeling hungry, will try to gain access over the chopstick, right? And eating process will include picking up the chopstick, right? So here the operations that are associated is pick up and put down. So in the state of hungry, pick up operation will be invoked, right? So here we have the structure of this pickup operation. Void pickup int I may take any number. Then state of I, if state of I, that I is indicating the philosopher. If one of the philosopher is hungry, its state is hungry, then we put test over I, and if state is not eating, then self, that means we are here invoking this thing, right? Self of I dot wait. Okay, so this in, if it is not hungry, then self of I will be taken to the waiting situation, right? Then put down is again a function here which is performed over I again. Then checking the state of I, if it is thinking, then test left and right neighbors. We need to perform test over left and right neighbors of this philosopher, what they are doing, right? So test over I plus 4% 5 and test over I plus 1% 5. If this philosopher is thinking, there may be a need that the other philosopher is hungry and will be picking up the chopstick. Then we have test function which checks the state of the philosopher, whether it is not equal to eating and is equal to hungry. And see here, now here you need to check the state of the 2 neighbors, right and left, of a particular philosopher. Okay, if this philosopher is hungry, it requires 2 chopsticks, one from the left and one from the right side. But if the neighbors are hungry too, they will be using the chopstick, so chopstick is not available to this philosopher who is hungry right now. Okay, so it is essential to check the state of its both the neighbors. Okay, so here we perform checking the state of the neighbors again, and then we have an initialization code. Okay, I hope you got this idea. Now each philosopher I invokes the operation pick up and put down in the following sequence. Now the operations pick up and put down should execute in a sequence, right? So here dp.pickup I, then eat dp.put down I. That means while taking this, when it is feeling hungry, it will invoke a pickup over the chopstick and will continue eating. As soon as it is finished with the eating process, we'll put down the chopstick again. So it should execute in a proper sequence. Here we have an implementation of monitors using semaphores. So variables include here semaphore mutex, which is initialized to 1, semaphore next, which is initialized to 0, and here we have an integer counter next count, which is again initialized to 0. Now each procedure f will be replaced by each of the procedure f will be replaced by this following statements, right? Wait mutex. First you'll need to perform a wait over mutex, since you need to gain access. Okay, so then comes the body of f. If next count is greater than 0, then it will signal next. Okay, so next is again a semaphore. Now signal operation will be carried out over next semaphore. If this is not the situation, then signal operation is carried out over mutex semaphore. Now this is mutual exclusion within a monitor. Here we ensure mutual exclusion within a monitor. Now for each condition variable x, we have semaphore x sem, which is initialized to 0, and int x count, which is also initialized to 0. Now the operation x dot wait can be implemented in the following manner. X count is incremented here, x count plus plus. If x count greater than 0, then we invoke signal over the next semaphore, else we invoke signal over mutex. And then we perform wait xm and count is decremented by 1. Now in case of signal operation, we can implement it in the following manner. If x count is greater than 0, then next count will be incremented and signal over xm is carried out, then wait over next, and next count is decremented again. Now here we discuss some of the synchronization examples. We can see how synchronization implementation is carried out in Solaris operating system, Windows XP, Linux. In Solaris operating system, synchronization implements a variety of locks to support multitasking, multi-threading, and multiprocessing. It makes use of adaptive mutexes for efficiency when protecting data from short code segments. It also makes use of condition variables and reader-writer's lock when longer sections of code need access to the data elements. Further, making use of turnstiles to order the list of threads waiting to acquire either an adaptive mutex or reader-writer lock. Whereas Windows XP uses interrupts mask to protect access to global resources on uniprocessor system. In case of multiprocessor system, Windows XP makes use of spin locks. Windows XP also provides dispatcher objects which may act as either mutexes and semaphores. Now dispatcher object may also provide events. Now events act like a condition variable. In Linux synchronization disables interrupts to implement short critical sections, and it provides semaphores as well as spin locks. In case of Java synchronization between threads, we have here some class. As Java is purely object-oriented programming language, it makes use of classes and objects. So here we have public class, some name of the class here, and public synchronized, here we have a method safe mode, right? So this is the structure of Java synchronization. In pthread synchronization, API is operating system independent here, and it provides mutex locks and condition variables. Non-portable extensions include read-write locks and spin locks. Now this is again a continuation of P threads here. I hope you have understood today's point that we discussed. See you in the next lecture.